Entanglement suggests that the universe isn't stitched together the way we think it is, that something deeper, something stranger, might be connecting distant parts of reality in a way our classical intuition can't explain. Today, we're lucky to be speaking with someone who has spent years tracing this rupture, and not through speculation, but through modern physics that forces us to rethink space itself. George Musser is an award winning science writer and former editor at Scientific American, whose work focuses on the conceptual edges of physics. He's the author of Spooky Action at a Distance, which explores non-locality and the hidden architecture of space and time. He also recently wrote Putting Ourselves Back in the Equation, where he looks at why the observer may be essential for understanding the universe. He holds degrees in electrical engineering and mathematics from Brown University and did graduate work in planetary science at Cornell. Thank you so much for joining us today. I'd like to start by talking about what first drew you away from studying about Venus into the world of quantum mechanics and, in particular, entanglement.
Yeah, so it's definitely been a continuous path. There wasn't like a sharp break, really. So when I left graduate school and went more into science writing, science communication, education, I started really writing about planetary science. So the things I had studied before. But like many of us, I've always had multiple interests. And certainly as a student, a student in physical science, you do learn kind of the foundations of physics, chemistry, etc., which includes quantum physics. So I always had tucked in the back of my mind some of these foundational questions about what quantum physics even means. I had a friend in graduate school who actually had done his master's degree on the philosophy of quantum mechanics and who kind of enlightened me about that's a strong term, but told me that, a lot of the things you learn in the textbooks doesn't reflect the kind of richness of the subject and the richness of the thinking. So he's the one who kind of first made me realize that there was more to it. And then that kind of started my own explorations. I talk a bit in my books about other kind of episodes. There were lectures I went to by Sir Roger Penrose, among other people, and that got me interested. But then I kind of really bracketed or shelved the idea for a number, or the ideas of quantum physics for a number of years. And it was really only coming back to it through the program to unify physics. In other words, string theory, other attempted unifications of all of physics into a single kind of unified theory that then reanimated my interest in quantum physics, because those theories clearly depend on quantum physics and what it means.
Well, I'm glad you did. The book
Oh,
was
you're
really
kind.
good.
Thanks.
So, before we go deeper into your book, could you set the stage for the early days of quantum mechanics and what it was that Einstein later called spooky action at a distance?
Yeah, so quantum physics was first really introduced just over, I guess, 125 years ago now, as an attempt to understand microscopic objects, the nature of particles, atoms, etc., the nature of light even. And it became pretty clear to Einstein and many others, Max Planck was another early innovator, that the rules that we see applying to the macroscopic world, the world of planets, and ourselves and so forth, kind of seem to lead to some paradoxes or riddles when extrapolated to this microscopic realm. And I should just jump ahead and I'll just foreshadow the idea that actually the things that apply in the microscopic realm also turn out to apply in the macroscopic realm. So there's not a neat division. But historically, quantum physics was initially conceived of as this kind of microscopic theory, and then later became a theory really of all objects. And I would say the central observation principle here is that objects have this dual nature, that often they behave like particles and sometimes they behave like waves. So the particles, what does that even mean? A particle just means a localized object, a thing that doesn't have to be literally an electron. or a mote of dust. It could be really just any body taken it could be our own bodies, for example, or a book, a rock, anything. But it's considered to be kind of an object that has a position in space. It has maybe some kind of lifetime, so some position, as it were, within time. It has certain properties. It has colors, shapes, etc. And then the aggregation of those properties gives you the nature of a larger object. So, like if you smash a Lego house into bricks, so I think that's kind of the Lego principle applies here. So then that's the particle side. That seems to work quite well. And the other side is this wave side. So what is a wave? A wave is a kind of distributed structure, as it were. It doesn't have one location. If you talk about a water wave, it's spread out over, a vast distance. A sound wave spreads out over initially the length of like a string of a guitar or a violin, but then over the room that it's in. So waves have this kind of distributed property to them. Waves are often thought to be derivative from particles. So this was like the intuition about air waves, sound waves, I should say, acoustic waves. You think of them, or to the extent you do think of them, a physicist thinks of them as the vibrations of air molecules, for example. But in quantum physics, the wave doesn't seem to have any deeper description. It's just a wave. It's just there as a wave or as a particle. So you got this dual description of nature that seems somewhat in tension of one another, and kind of the quantum mechanics has been the effort over the since 125 or whatever years to make sense of that dual description. And one aspect of it is that, and this is, as you say, Einstein really was the first to appreciate it very early on, actually long before quantum physics was even formulated as a theory. This was like an early intuition that he had back in the early days of the 20th century, is that because a wave is distributed, you can have connections among different parts of a system. So that's what a wave actually really is. It's kind of a core on separated places in space that a particle doesn't have, because a particle is just sitting in one location. So Einstein recognized a variety of phenomena, including the one we call quantum entanglement, but there are other phenomena as well that come from this distribution issue. The fact that one location in space can connect to another.
And is that what led him to write with his colleagues, the EPR paper?
So the famous EPR paper in 1935, which has become since then one of the most cited papers in science generally. At the time, it was kind of almost regarded as a novelty, though. But it was extremely profound. And it came out of earlier work. As I said, Einstein had been thinking about this by that point for close on 30 years. And the idea is that you can have two particles. In this case, they're photons, but they could be electrons. It could be really anything that have a common origin or a common point where they were touching, or maybe they even originated in one place and then sped off in two different directions. And if you measure one, you can learn something about the other. And you can learn things that you couldn't learn if the objects obeyed purely kind of traditional classical Newtonian physics. So in particular, one thing that happens in quantum physics, and this is kind of a precursor to that paper, was there's a random element in quantum mechanics that if you measure, let's take position, it could be here 50% of the time, on the left side, on the right side 50% times. And there's kind of no way to know that in advance. It's decided at the moment. It's a purely random outcome. I actually compare it to a coin toss. It's quite similar, actually statistically, to a coin toss, but there's a dice roll, a roulette spin, anything is quite analogous to that. So you got this randomness and you have this correlation. That's the tension. If you didn't have this inherent randomness, then the correlations would be not mysterious at all. Things are always correlated. The example people give is the socks in my drawer are paired up by color, etc., size, color. So I pull out a pair of socks and I put one in each hand and okay, they're correlated. They're either identical or, depending on the sock, you have a left or right kind of shape to them. That's because when I folded the socks, I set it up that way. It wasn't a random outcome. In other words, it was something that's kind of pre-decided. But in quantum mechanics, things aren't like that. They are actually decided at the moment, actually really at the moment of observation. That's a whole other can of worms. So this coexistence of randomness with synchrony is really the defining mystery. You call it a mystery, defining riddle, unresolved issue of quantum physics.
And one we're still discussing today.
Still being discussed today. And it's one of these things where everyone says, I know what the answer is. And they give an answer. And, oh, I know what the answer is. They give an answer. And then you get a room full of 10 people. They have 15 different answers.
Exactly. Maybe we could define locality, non-locality, and entanglement.
So entanglement and this specific issue I'm bringing up of the asynchrony, despite the randomness of quantum outcomes, is an example of what in physics we call, or what in philosophy also we call, non-locality. And I alluded to it earlier when I talked about waves. Waves are a non-local phenomenon. It's something that doesn't exist in one location. It's kind of spread out and has properties. And actually, a wave, technically, the waves we idealize in physics are infinite in size, so they extend across the solar system and beyond. So non-locality, you really have to define locality to understand what the non-locality is. So locality is a principle or principles that, first, things have positions. They're kind of well-defined places that you can situate them in. The kind of other aspect of it is not only do they sit in certain positions, they interact with other objects by sending out some kind of intermediary in space. I mean, if I want to send an old-fashioned, postal service letter to my friend, I have to write it on a piece of paper, I put a stamp on it, envelope, send it through the mail. Someone carries it across the country to the other person in the mailbox. They open it up. And email is actually no different, or text messaging no different from that, except it happens not with paper, but with electrons. So there's always a connection between things that are situated at different positions in space. That combination of those two principles of situatedness and kind of interaction or interactivity is what we call locality in science, or in philosophy of science. And non-locality is the violation, and there's multiple ways you can imagine a violation of that. You can imagine a violation of things aren't in one place, and the other side of it, that even if they are in one place, they're not communicating by sending it's on an intermediary, or communicating by passing through space. So this is really, I think, was kind of one of my first epiphanies or Archimedes type eureka moments when I was working on my book, was that locality and non-locality are really defining what we mean by space. What is space? Space meaning like the space we all walk around in, not just outer space, but all space. And that is it's defined really by locality. So behind me are books on a bookshelf, and it's not just a Zoom or electronic version of that. It's actually really, these are books on my bookshelf. So there are different positions on the bookshelf. So they're kind of defining the space of the bookshelf. There's a book on this side, there's a book on that side, there's a book in the middle. So they're filling out the space in there, and that's locality is essential to that. Because otherwise, if they didn't have positions, I wouldn't know where to find my books, of course, in that case, but also they wouldn't really be spatial in a way. So locality and non-locality are bound up with what we mean in science and in philosophy by space. And also time comes in there, but in more subtle ways. And then quantum entanglement, seems to violate one or both aspects of locality. Ergo, entanglement is non-local. Now, it took physicists really a long time to really come to terms with that, because earlier they said, yeah, it looks non-local, but it's really local. This was Einstein's original intuition, and he came up with different ways it could look non-local, despite the fact it is really local. But I think what we've learned in the intervening century plus is it really is non-local.
Yeah, my next question actually touches on that, because for a long time it was just kind of found in mathematical equations. But then a couple decades later, experiments started showing that it may be a real tangible piece of our reality, and that scientists had to start dealing with it. Could you talk about the first experiment that proved entanglement may be a real phenomenon, and how the scientists reacted?
Yeah, so it's one of those things where it's not really one experiment. this is why it's kind of fun, actually, because there's a dialogue. It's kind of a dialectic here where someone says something, they do an experiment. They have to revise what they said. They do another experiment, and it kind of stair steps up. Einstein, first of all, I should say it. The phenomena that we talk about when we talk about quantum entanglement look non-local. Just if you did it, you would say it's non-local. So then, so the experiment shows it immediately, and experiments can be done with photons, with other particles. That you measure different places, and they have this property. And I can come back to that, but let me just go through the kind of progression first. So then you would say, or not just you, Einstein, Bohr, these people said, yeah, it looks on the face of it non-local, but you shouldn't trust your first impressions. You should say, it's really local. And the principle there is similar to this principle of socks. You look for the explanation went that the particles, when they're created, are created with certain properties that they carry with them, no matter where the particles may go. And when you eventually read them out, have this correlation, have this kind of synchrony. Yeah, something I really should kind of be more kind of concrete about this. And I really do think coins are the best way to get at this. The particles are obviously literally coins. There are a lot of differences actually from coins, and not least that they're tiny and not made of metal and all that. But the idea of flipping a coin actually, and the statistics, the randomness involved in that actually does match what's a particle. So if you imagine you flip a coin, it's 50-50 outcome, right? And it should not be correlated. It should just be flip it, and 1,000 times you get roughly 500 heads, 500 tails, etc. It, by the way, never is exactly that because it's random. So you're going to get maybe a little bit more, a little bit less. So if you imagine flipping two coins that you presume have no connection between them, again, they should independently be 50-50 on each side. So you imagine that they're both coming up with the same answer. I guess it's also 50% of the time. So you might get two heads, two tails, or one heads and one tails and one head. So, and they do that, I guess, half the time. Or they're the same half the time. So they're either both heads a quarter of the time, but you can kind of work through whether they, and we call this a coincidence in physics, whether they have the same outcome on both sides. And so you do this with your quantum particles that are not entangled. So there's always the option in quantum mechanics of not entangling them, just treating them normal classical like objects. And if you do that, it matches those statistics. You flip the particle, the coin, and that the word flip there is hiding, experimental procedure but it's no different in kind of outcome than flipping a coin. And you would get, 50% heads and tails on one side, 50% on the other side, statistically. And usually we have to think about this statistically, and they're the same outcome half the time. So with a quantum, if you had a pair of quantum entangled particles, now you do kind of imagine giving them this property of entanglement. And there's, again, experimental ways to do that, very interesting ways. Then you flip them, and maybe 100% of the time they land on the same side. Or usually it's not really 100%, it's more like 85% of the time they land both heads, both tails on both sides. That violates your expectation from probability. So this is the kind of experiment that is done. All right. With that experiment in mind, you can kind of go back and think about what Einstein and the others were saying. So they were saying, okay, yeah, it looks pretty weird, right? That, if this happened, you would assume, what would you assume? You would assume that someone has gimmicked the coin. It's like a stage musician has like tinkered with that. And actually, when I was doing this and doing talks on this, I actually went to a magic store in New York and bought a bunch of coins that are trick coins. And there's different kinds. One kind is just, it's a double-sided coin, right? It has like heads, it's heads, or tails. So you can kind of, if you do a little sleight of hand, you can kind of fool people into thinking this. So you might imagine there's like that kind of thing going on. There's no one person trying to fool you, but maybe the particles, there's something about them that fools you in a sense. You think that they're behaving in this correlated way, um, through some kind of ineffable force or ineffable influence, but they're really like a trick coin. There's like something, like some trick to it. And one way that trick might work is when your particles are created or initially interact, they jointly kind of decide. I'm anthropomorphizing, but they basically decide between them what they'll do. Hey, we'll both be heads, we'll both be tails. And again, you can kind of take those anthropomorphic terms and put that into actual non-anthropomorphic terms, but it's kind of the same idea. So there's kind of a decision or kind of a process that occurs that synchronizes the coins. But then the key is that they carry that over the distance. So they retain that knowledge, or they retain that kind of property. And that's retention of property is what the experiments have cast out on. That those are really experiments that, guess the late 60s, they were envisioned in the mid 60s by John Bell, who's a physicist whose name comes up in this context. He was kind of the champion of this whole field in the 60s. And I think the first one was done in like 69 or 70, and then up to the present day. I've done the experiment myself. It's actually becoming an undergraduate project in some places. So it's cool. And then that shows that no, they can't retain the property from the beginning. There's kind of a break in what happens. And then there's multiple other possibilities you can investigate. Each one has been struck down. So kind of at the end of the day, you're left with, yeah, it's got to be non-local.
I know that's the one that my brain had the hardest time dealing with. I just liked it when I pictured they had their properties, they moved to be measured, and they retain the properties the whole time. So, yeah, that's when I learned about Bell's. Is it inequality or?
Yeah, so the inequality, just a mathematical expression of that intuition that you would expect something from probability theory, essentially, namely roughly 50-50 outcomes. And there's more to it, but this is the basic idea. And then in quantum physics, you can violate that. So that's expressed mathematically as an inequality. It's sort of like an equation, but just with a lesser than sign, a less than sign.
It seems like at this point we've accepted entanglement as a fact for the most part, and now we're more debating what it actually means, especially in the different circles and interpretation of quantum mechanics. Could you dive into a couple of the uh, interpretations of quantum mechanics and how they view entanglement?
Yeah, so this is super interesting. Just as a kind of like quick 2-second digression here. In addition to the theoretical foundational work that, we're both of us are so fascinated by, there's also a huge practical set of work here that actually doesn't really depend on the spin you put on this, kind of the understanding that you achieve. So you can use quantum entanglement for cryptography. You can use it for, you can't communicate entirely with it. It still requires always a regular kind of communications system setup, but you can bolt it on to your communication system and either make sure that it wasn't tampered with on the way. So it provides secure communications. It can provide ways of augmenting your communication channel, kind of packing more information in. It can be used, and it is being used heavily in quantum computing. So it's one of the reasons that quantum computers have kind of more storage capacity bit for bit than a regular computer. It can be used in the processing that quantum computers do. So yeah, it's a huge field that, often in science, history of science is more 2 seconds, so bear with me. It's really the engineers who push it. So thermodynamics, one of the great accomplishments of the 19th century in physics and human thought, really was Johnny come lately to what the engineers were doing, building steam engines. So the physicists came in, years, decades after the engineers had actually kind of already done it, and they put the theoretical gloss on what a steam engine does. And of course, it doesn't apply just to steam engines; it applies to cells, to computers, everything. With quantum entanglement, it's almost the other way. It was theorized about way before the engineers got involved, and I think that's kind of a cool and kind of unexpected turn of event in this field. Okay, so what does it mean? How can particles retain this, I call it a connection, but the synchrony of properties between them, such that, as with coins, if you flip them, they come out the same on both sides. How do they do that? and there are a lot of options. I'll just cut to the chase and give you my favorite one, or one that, well, I like them all, but one that I think uh, is a leading contender, and that it's telling us something about space. Remember, I think this issue of locality is tied up with the nature of what space even is. I think my hunch, or a possibility, is a live possibility, is that quantum entanglement reveals that space is not fundamental to the universe. There's something deeper than space, and the entanglement is sensitive to it.
Yeah, that was one of my favorite parts of your book was learning about the different theories that have come about for their own reasons, a variety, and how they all seem to show that space time may be emergent and not fundamental. I think you talked about holography, black hole thermodynamics, information theory, and quantum gravity.
And I think what's cool, if it were just entanglement, it's such an awfully slender pillar to, dethrone all of space, or whatever the mixed metaphor would for that should be. And it's you want more than that, and that's why I brought in those other fields like the holographic principle, as you say, cosmology. There's issues there. There's in particle dynamics. There's actually a lot more even. So all these different sub branches of physics are kind of telling you the same thing in a way, in different ways, but they're leading in the same direction, shall we say, or they give you the same spirit of outcome, which is that there's something about space and maybe even time that is derivative, that it comes from something deeper. So you get this definitely with black holes, as you rightly point out, and there's other gravitational phenomena and other physical phenomena that we have, other astrophysical and cosmological phenomena as well. So you get this kind of multiple uh, lines of evidence leading us to think, leading physicists and humanity broadly to think that space is a derived feature of the universe, and there's something deeper out of which it comes. And I mean, obviously, that would help you with the Big Bang. It would help you with the origin of the universe, because you can imagine the Big Bang was the assembly of these deeper ingredients, whatever they may be. We have no idea, uh, into space. And the Big Bang, people have developed ideas, would then be thought of as like what we call phase transition in physics. It's like a freezing or boiling or a condensing. It's something like a change of state. So our current universe may be the outcome of a change of state of these fundamental ingredients. Now, the other, but that by no means is that a settled issue, and there's many other interesting interpretations of quantum mechanics that you mentioned that there are. I think they all lead us to question space and time in some way or other, but maybe they do it to different degrees. So another kind of almost fun one, although it's taken very seriously, but it does sound kind of funny when you first encounter, is what's known as retrocausality. And this is idea that there are influences traveling backwards in time. Normally we think of like what happened today, depending on what happened yesterday, depending on what happened the day before. Everything is like causally forward in time from past to future. But why, or could there be influences from the future that influence the present, that continue to influence the past? So it's sort of like the movie Tenet, which I really liked. It blows everyone's mind that in that movie there were influences from the future affecting the present, and how weird is that? Um, Probably doesn't happen very much. Certainly not to the extent you have in that movie where you have bullets and things flying backward. But the one place where it might be potentially observable, where might have a future to past causal influence, is in these quantum experiments. They're very controlled situations. So they're the kind of place where you might, in principle, glimpse this backward in time effect. And the way that kind of works is, one thing I didn't mention earlier about these experiments is you're making decisions in these experiments. Part of the statistical outcomes come from some kind of decision that you have to make about what to measure. Like, do you measure position or do you measure velocity? Do you measure spin? That's one of these properties. Do you measure spin on the x-axis or the z-axis or the y-axis? So those decisions condition the outcome of the experiment. And those decisions are made after the particles were initially created. So by your standard notion of causality, our decisions shouldn't affect how the particles were created because they came after, right? So the proposition is that the decisions you make about what to measure, X or Z, or particle velocity versus particle position, actually do go back in time and affect how the particle was created. And therefore, the particle kind of knew, in this, again, anthropomorphic language, kind of knew what would happen and was prepared for it. And yeah, it sounds weird, but I think one lesson of quantum mechanics is it's weird in some way or other. Either you get the breakdown of space time, you get this backward in time thing, then there's other oddities as well.
Yeah, some of the experiments seem to provide that evidence. It's just hard to conceptually deal with it.
I think so. And I think it will lead to kind of new physics directions, maybe help us with this unification problem that's been so vexing so long. So I think it, there's a complex of issues that we may even need unification to solve it, actually. But anyway, this is like very frontier work. Um, it is difficult. It should be difficult to get our minds on. Our minds evolved on the savannah or whatever. We'd evolved to deal with conditions on Earth. These are very kind of foreign conditions. So in a way, our brains, it would be surprising if we did understand it.
How does the many worlds interpretation explain entanglement or look at it?
Yeah, this is good. So there's different ways to think of the many worlds interpretation. Let me start with the most common, but then I'm going to later kind of backtrack a little bit on that and kind of go to what I think is even a more essential element of it. But anyway, the common view is that there's our kind of branching effect that we live in what we call multiverse, that it consists of countless, literally countless parallel universes. And you get this in science fiction all the time, right? So there's parallel universes out there, and the proposition is that the puzzles of quantum mechanics have to do with that multiverse or parallel universe structure to reality. That, for example, when I flip a coin and it randomly comes up heads versus tails, it's really coming up heads in a bunch of those universes and tails in the other set of universes. And ideally, you would want to just say half of the universes it's coming up heads, half it's coming up tails, and that would match the probabilities that we observe. And that's the intuition there. It turns out actually those probabilities are kind of very tricky to assess, and hence this is still an active area of research is trying to understand what does probability mean when you've got a whole like infinity of these parallel universes. But that's the basic intuition, and then either those universes are just there already, and we have gaining access to them, or losing access, or our access is varying, or they literally are created. And one of the versions of this direction is that when you measure a particle, you cause it to branch. So you kind of brought those universes into existence. Anyway, there's different ways of kind of perceiving this. It doesn't entirely solve the question of non-locality, or the understanding of entanglement, because it kind of pushes it onto how we define these universes. So what is a universe? So you'd have to kind of articulate that universe is kind of this structure, has some coherence to it. It isn't just a hodgepodge of matter. Obviously, it has some kind of a causal structure, and the universe has a star in it. Things go around the star. I mean, you have to really kind of pin down what you mean by universe, and in so doing, you kind of have to contend with this non-locality question. So it's kind of built into the universe definition. I guess that's the kind of most straightforward way to say it. There's obviously a lot of mathematical complexity there. So this is a very powerful way of understanding the randomness of quantum mechanics, but it doesn't really help a lot with the non-locality question. It just kind of, it's like pushing on one side of the balloon. You just transfer the problem to the other side. Now, I said earlier that I think the many worlds interpretation has this kind of parallel universe gloss to it. That's very interesting, very cool, very fun to think about. It's also, God knows how many novels and science fiction shows are based on this. And I eat it up. I love this stuff, like sliding doors. That's the classic one that everyone talks about. But there's lots of others. But I think sometimes the original insight of Hugh Everett, who was the physicist to develop this idea in the 50s, was kind of lost. And It was lost even in his own time, which was sad because he got so just annoyed at everyone for missing the point, is that he left physics and went on to develop nuclear weapon strategy for the Pentagon or as a contractor. So he went like literally he did something completely different in his life. Um, and he, by the way, argued that we should not launch a nuclear war, which at the time was not an obvious thing to say. A lot of these people actually really did want to go at it. So we should be thankful that maybe he was kicked out of physics and kind of bring some restraint to what would have been, our end probably. So his original insight is you have to be very careful about understanding your observations. So basic point was we flip a coin, or a particle that acts like one, and it comes up heads. And we wonder, how did it come up heads? Oh, there must have been something happened to make it come up heads. We call it quantum collapse, for example, or we just give a name to it. But there's something that the particle originally was in this ambiguous state of heads and tails, and then it snapped to one option or the other. That's what we observe. So Everett said, that's what you observe, but are you really sure you know what happened to the particle? So you think it snapped to heads or tails, but what if the particle continued in its heads or tails ambiguity? This particle started out kind of indecisive. What if it continued to be indecisive? In other words, nothing really happened when you observed it to the particle. The only thing that happened is you saw it to be heads or you saw it to be tails. So it's really a question about you, the observer. This was his central insight, that a lot of these questions of quantum mechanics have to do with the observer. When we observe, we take off our glasses or we put on like colored glasses, rose tinted glasses. We see the world differently. We think we have access to the world, and we all know we don't. We all know that, God knows all the ways that our view of the world is biased, right? We're biased by just, culturally biased. We're biased by the fact we see only visible light. We don't see the other forms of light, like infrared. We're biased by our temporal window. We see events that take place over a second. So we don't see the tectonic plates moving directly. We don't see the fly wing beating. So we're very limited in our human capacity. And Everett's point was that physics also needs to take those limitations into account. So I just wrote a whole book about these limitations. That was my most recent book. And I talk a bit about how it might affect our view of these quantum experiments.
Definitely something to consider. The more you learn about perception, the more you realize that there is no way you see reality as it is, that you're not observing things as they are. So how do you interpret what it is you're seeing in a scientifically accurate way?
Yeah, I really think cognitive psychologists have known that. I mean, probably most people realize it. And ironically, it was the physicists they were the last to learn. They were the last to kind of figure out. And physics has in its DNA this idea that we're observing the objective universe. I still think we are to a degree, but we're observing it through our filters. So anyway, that was, I think, the kind of origin, the genesis, you could say, of the many worlds interpretation was you need to take into account the nature of observerhood. And then that theory went into a lot of different directions. The most popular one is this one we call many worlds, but actually the overall kind of collection of ideas we call Everettian, the Everettian view, of which many worlds is one case. But there's many, many other cases. And I hope on this program, you'll interview people who were advocates of one of those other kind of, approaches. Well, Carlo Rovelli is the one that I've talked to Carlo about this going on. When did I first meet Carlo? 20 years? Was it 20 years ago? Almost 20 years ago. Wow. I should have an anniversary celebration.
You should. He's great.
He's great. He's super innovative. He writes amazing little books on this that have inspired me. And he and I have had long discussions on this very question. He has his own kind of idea of, it's a broadly Everettian view. It has its own distinctive aspects having to do with conceiving what is a property in nature. It has to do with, again, the act of observing, and he understands active observing. He has this whole idea about that. I think where he and I differ is just that I'm willing to consider other views as well, because I'm not really committed to one. I don't think that's really my job as a science writer, is to come down strongly in favor of one or the other. I kind of think And I do really genuinely think they all have valuable insights to play. And maybe some will be wrong or maybe partly wrong or one will kind of stand out, but we're no position to decide that just yet.
Well, and that's science, and it's very helpful to have someone put all the theories forward so we can do research, learn more, and decide for ourselves.
I think so.
Oh, I appreciate it. One thing I wanted to ask you is it seems like in pop culture and in general discussion, the term entanglement gets used pretty loosely. Are there any common misconceptions about entanglement that people should understand?
Yeah. I mean, I guess I'm not too much a stickler on this. People have appropriated or co-opted lots of terms from science. Like the one that actually does kind of annoy me sometimes is epicenter. So an epicenter is a geologic term for the point on the surface above where the earthquake took place. So it's meant to be a kind of, it's not literally the center, it's the epicenter. It's the thing that we can see on the surface. So a lot of people just take epicenter to mean center, right? So it just happens a lot in science. And it's kind of funny actually that these words get misapplied. I don't know if has it really happened with entanglement in a way. I guess superposition or Schrodinger's cat is something that maybe we talked about Schrodinger's politician. Politicians believes something on the right or and the left at the same time. Maybe we use it. I mean, I probably made that one up, but there's other cases where we talk about Schrodinger cats. This idea of cats that are both alive and dead. Um, Schrodinger cat, of course, is super interesting case in its own right. It goes back to what I was saying. It's similar to this coin issue. Um, and probably the term isn't strictly applied in the correct way, but I'm like, whatever. I mean, knock yourself out if you want to use it to mean that. I'm not gonna not gonna say no. Were there any
Yeah.
misconceptions that you had in mind that you wanted me to
No,
analyze?
sorry. It was kind of a general question. I just seem to see it more in maybe new age type posts and things
Ah,
like that. People being entangled or such and such happened because they must be entangled.
I mean, again, it's one of these things where I think there's a germ of truth in those things. We are all entangled in the physics sense, and by the way, much more significantly in a social and biological and cultural sense. So I think if we're going to talk about uh, reasons that people have a melding of the minds in this sense, I think I would look to psychology and sociology for that. But we still are entangled physically, and I think that's super interesting. The thing that doesn't happen, and I think people kind of don't realize, isn't so much that there is an entanglement, but it's the degree of it. So if you're going to say, "Oh, I feel my my loved one's pain over a great distance," or I feel something happened to my child, it must be quantum entanglement. It's probably not for a number of reasons, not least of which you're also entangled with everyone else on the planet. So you would expect to feel everyone's pain if that were really the case. There's nothing privileged about any one of those quantum entanglement kind of relationships. So I just think we need, and this is a general principle in life, we need to look to the appropriate level for the answers that we seek. I don't think physics is wonderful. I love physics. It tells us about ourselves at a very deep level. It tells us where we came from. But we don't want to overread too much into it and say, well, all the mysterious phenomena of the world must be physics. Most of the explanations for why things happen, like you bump into a friend you haven't seen in 20 years on the street. That actually just happened to me recently. It just happened, maybe there was something that brought both of us to that point, but that wasn't physics that did it. Another one, I guess, maybe in the line of what you're thinking is fields. People talk about fields and energy fields. And I think there's a real sense in maybe in which our bodies and our medical practices can be described in terms of energy fields. It's probably reflecting something about our makeup or physiology, but it's definitely not the fields we have in physics because a number of reasons those fields are pervasive. They're all over the place. The electromagnetic field fills the universe. So it can't be that because it's too non-specific to the human. It also occurs on the moon, everywhere else. So I don't think quantum fields, by the way, it's not even really understood what quantum fields are. So I definitely wouldn't hang any explanation on them. Anyway, I hope that kind of gets at what you're.
I was curious after spending so much time looking at quantum mechanics and everything that's come with it, how has it shifted your view of reality? Do you see the world any differently than when you first started?
Yeah, I mean, I'm one of these people who's always thinking about these things. It's very important to me, just as a person, to know I'm part of something like bigger, and then to have some kind of comprehension of that. It frames my daily life. So I think my life would be different if I didn't know about the solar system or the fact I'm on a planet versus just like at the center of the universe or whatever. And likewise for entanglement. I wouldn't say that it does anything super specific. It's not like, entanglement. It's more just like a general framing of my worldview. I'm also framed my worldview and my kind of approach to life is framed by many other things. I love hiking. It's very important to me to be in the natural world. So being part of an ecosystem is also super important to kind of my self definition. Even if it's not that practical, I think it's important just spiritually, as it were, to be aware of these connections and of this kind of situatedness that we have, be it biology, be it nature, be it physics. Why choose? I mean, just do them all. I think it's important to know where we are in the universe. When I look, and I was just observing with a friend of mine up in Northern Ontario recently, we had a beautiful view of the sky and we looked out at the galaxy and to the planet, and Saturn was kind of up in the sky at the time. And just to know that I'm looking at Saturn across millions of miles of space just was so cool to me. So I guess entanglement is kind of the same.
I enjoy these topics because of that, especially the emergent space time and just picturing how things are really put together. What is space, the relational aspect of everything? It makes you kind of see magic in the world, I guess, is
Yeah,
a way to see it.
I think that's a beautiful way of putting it. Yeah, totally. And it gives you a sharper feeling of what is magical. Maybe that's actually not to be too analytic about it, but to and this is something I talked about in the spooky action book. The and it was in the context of like ESP, so and these kind of supernatural phenomena. And if you kind of work through what ESP would act if it were real, would actually mean, and if it were common and real, would actually mean, it would actually be terrible. We'd all be reading each other's thoughts. Nothing we do would really even begin to matter because you could just imagine. It's like Harry Potter world, and the Muggles kind of have it really bad, right? They can always be overridden by Voldemort or something. So likewise with ESP, we have to be really careful. We probably lose control of our own internal thoughts, right? That kind of magic, appealing though it is, ESP of whatever, would actually be something we wouldn't really want to live in that world. So I think, um, then therefore, what is the magic? The magic is that we live in a world of locality, that the universe somehow probably is fundamentally non-local, but became local, and then that allowed for us. Our life depends on the universe being local. Our life depends on there not being strong ESP. Maybe there's a little bit, but as long as it doesn't, you know, overpower our cognition or allow kind of weird things to happen, like bad weird things to happen. I think anyway. I'm not probably making any sense. I just think,
Well, it does make sense, and even just an evolutionary standpoint, that if we had the capability, especially for emergency situations, be aware of patterns, be extra observant, maybe a little whisper of non-locality, it makes a ton of sense that evolutionarily speaking, it would be a survival tool, is kind of how I look at that. But I completely agree with you. I don't want to have everybody hear my thoughts or hear theirs for that matter. Just my mind alone is busy enough. I don't need others.
exactly. So it's not gonna put bread on your table, but it's definitely, I think. I mean, we humans are about more than that, right? We're trying to understand one another. We're trying to understand the world we live in, and to me, the understanding quantum entanglement is part of that. It's just as important as like understanding the natural environment, understanding our cosmic environment. This is our kind of reality environment. This is kind of like the nature of the reality that we're a part of.
And there's a lot of practical uses of it as well, not just theoretical. When you were talking about the current technology that we were using this entanglement for, where do you see it going in the future? Do you think that kind of where we are is about as far as we can take it, or are there some ideas that are just going to blow our socks off?
Yeah, so interesting question. I do think you could say a better understanding of entanglement will help with these engineering and technologies and so forth. I don't think it'll help with the foundational question of what the heck it is to be entangled. But for instance, one frontier, both theoretically and technologically, is multi-particle entanglement. So usually, when we talk about entanglement, we talk about two particles or two entities. Like, that's how I've been framing it so far. We have two coins or two things that look like or act like coins. But if once you start putting 3 and 4 and 10, it starts to just multiply the complexity enormously, and you get all sorts of kind of collective effects from that. And in some ways, in some cases, also the collective effects may be directly visible. So it's not like it is. Entanglement's often kind of a hidden thing. It's there. In fact, it's really everywhere around us. It's just hard to get at. But there may be certain situations where you have these kind of multi-particle entanglement effects that they become more directly visible. Like magnetism may be one. It wouldn't just be magnetism per se, but just some of the properties of magnetic materials. So I think that will be super important. Again, computing, when a quantum computer stores information and usually just stores it across its qubits is the term. Instead of being composed of computer bits, it's composed of computer qubits, quantum bits. And usually the state of the computer is a collective state of all the qubits in the computer. That's what gives the system so much power. And the entanglement among the qubits is not just essential, it actually is the collective effect that I'm talking about. So yeah, I think when we all have kind of quantum processing units, I think that, our phones and our computers have GPUs, graphic processing units, or like gaming consoles have these GPUs in them. I think probably in 20 years, we'll have QPUs, quantum processing units that will be used for certain applications. And we'll have entanglement then on our desk in front of us.
I was curious as well. What is it that you have been researching lately? What has caught your curiosity? Any new books in our future?
Yeah, I'm thinking about biology a lot these days. I've I was lucky to have a couple of fellowships this past summer at two laboratories to kind of get my feet wet, actually, literally, in one case, and understanding the natural world. Because, um, it was a little bit like with my recent book that I wanted to think more about the brain and the mind, consciousness, and what does physics have, and how does physics help our understanding of the mind, and how does our understanding of the mind help physics? I think it's two directional. And likewise, I kind of want to repeat that trick now with biology, kind of understanding life. What is life? Like, what does it mean to be alive? And it's an incredible question, right? So it's hard to define, but it's definitely something that the living world is just a step change from the inanimate world. So what is that thing? And plus, it's just the incredibleness of it all, right? Just the things that living organisms, our bodies included, even just single cells can do. It's just you blows your mind. It's so cool. And you're the expert here on that. I'm just like a newcomer to a lot of these biological ideas, but I'm just like drinking it in. I'm just like kid in a candy store. It's just so incredibly cool. I'm like, whoa. My wife is like, whoa. She hears me going, whoa, what's up now? Oh, I just read this. So it's just I'm loving it. Plus, it connects with my interest in nature. You know, um, I've been section hiking the Appalachian Trail, so I like just um, taking that in. So it definitely connects with kind of my non-scientific passions as well.
All good thoughts happen while walking. So
Pretty much. In fact, you are more right than you. I mean, you have your own experience, but every time I visit a physicist at their lab, Carlo Rovelli, perfect example. What's the first thing they want to do? Well, usually get a cup of coffee and then go for a hike. Carlo and I went all walking all over the place. It was amazing. And I visited all these other people. First thing we do is get a cup of coffee, then we go for a hike.
that's great. Well, I can't wait to hear more about it. I hope you'll consider coming back and talking with us about new developments and your most recent book, Putting Ourselves Back into the Equation.
Thank you. It's really been an honor. I love talking to you.
Thank you, you too.